Welcome to part 2. This is part 2 of lesson 3. In part 1, we talked about some equivalent ratios, and we're going to spend part 2 doing the same thing, but with triangles. You're going to find out that triangles are not just shapes. There's actually some kind of magical things you can do with them. And once we get through actually getting introduced to triangles and how to name them and all that other good stuff, we're going to do some problem solving with them in real life scenarios. So hang with me. If you haven't already, I'm going to step aside a little bit so you can actually really see these triangles really well. And I want you to go ahead and copy these into your journal and make sure you write down these letter labels here. A, B, C, D, E, F, G, H, I, because that we're going to have to use those to name these triangles and their sides. Okay? So pause the video if you need to, and then we'll get started. Okay, now that you have these copied, let's practice naming these triangles first, okay? Triangles go by names based on their point or vertex labels. So the first thing I'm going to do, let's name this one here. I'm going to tell everybody this is a triangle by just drawing a little triangle symbol like this. And then I'm going to write these next to that. Generally, it should be in order. A, B, C. So the name of this triangle here is ABC, okay? This triangle here then would have the triangle symbol and D, E, F. We'll come back to this one in a minute, okay? I just want to talk about these two left triangles for now because we're going to kind of get this out of the way and then we're going to move on and spend more time with these guys right here. But I want to go ahead and let you know that these two triangles have the exact same side lengths. This side right here is exactly the same length as this side. These two sides are the same and these two sides are the same. And we're also going to go ahead and assume that all of their angles are the same as well. Okay? Since that's true, these two triangles, which are exactly the same, are called congruent. That's a word that we need to know. Congruent is a word that means same side lengths, same angle measures. Okay? And it has a cool little symbol if you want to write this down too. Congruent is an equal sign with a tilde on top. So what I just wrote here was that triangle ABC is congruent to triangle DEF. Same side lengths, same angle measures. In short, exactly the same. Now I can flip these things and rotate them and make them look different, but if they have the same side lengths and the same angles, they are congruent. Okay? Now I'm not going to spend too much time on congruent because I just wanted to get that out of the way. I'm going to delete ABC. Mostly just so we can focus on these two triangles here. Now these don't have the same side lengths, okay? The length of this side right here and this side right here can be written as a ratio, but they're not the same. I'll tell you what I mean by that in a minute. All of the sides of this triangle are proportional to the sides of this triangle. Proportional is a word that we saw in part 1. So they're not the same, but they are proportional. And I'm also going to go ahead and assume for these exercises that all of the angles inside are the same. They have the same angle measures. I don't necessarily say right here is a right triangle, but if it was, so would that be. Okay? Don't worry too much about angles yet. Let's worry more about the side lengths and their proportionality. Okay? So I'm going to go ahead and name these two. Again, there's DEF. So this is triangle DEF. So how would I write that one? How would I name this little guy? First, I need the triangle symbol, right? Okay. And then what? Did you say GHI? I don't think order matters too much when you're naming a triangle, but it's a good convention to stick to go ahead and put those in order, just so we don't all confuse each other. So here are their names. And these two triangles are not congruent because their side lengths are not the same. But since their side lengths, and I've told you this, are proportional, I can use just the little squiggly tilde to say these are similar triangles. Okay? These two triangles are similar. Now let's see if you, let's see where you're at with this kind of geometry stuff. Do you remember how to name just one side of a triangle? To name the whole triangle, we use this little triangle symbol. But what if I just wanted to name this side right here? From the F to the D. Do you remember? Basically, I would say DF with a line over it. That's how I name just this side right here. Okay? Now, I want to show that that side, this side right here, has a relationship with this side right here. Can you see why? Because with two similar triangles, each side is going to have a relationship with a corresponding side. All right? So DF, this line right here, has a relationship with GI. So I could write that as DF corresponds with, or to, I'll just put with, line GI. So there's a couple things I know so far. I know these two triangles are similar, which means all their angles are the same and their side lengths are proportional. And this little symbol right here shows that. Okay? Since I know these two triangles are similar, I also know that line DF corresponds with, has a relationship with, GI. And that relationship specifically is that these two lines are in the same position on these two triangles. Okay? Don't worry if you're not too much of an expert on this yet, because we're going to do some more practice as we go. Now, if DF corresponds with GI, then which line corresponds with DE? GH. These two correspond with each other because they're in the same position on the two different triangles. So finally, what if I looked at line EF? Which line does that correspond with? HI. Hi, HI, okay? Now, the nice thing about corresponding sides is that since they have a relationship in between two proportional or similar triangles, that means I can make ratios out of them, okay? So if I know that DF corresponds with GI, I can just write these as a ratio. Okay, can you see how this is a ratio in fractional notation? I can also show that DE forms a ratio with GH. So it's the last ratio I'm going to write. Take a second, go ahead and write down the last ratio for the remaining sides. Do we agree? Okay. So I have three ratios here for three different sides. Now, I can do all kinds of stuff with this, all right? Now I'm gonna go ahead and give these things some measurements, all right? Let's say, change colors here so it shows up a little bit better. Let's say that FD has a measurement of 8. And EF has a measurement of 5. And DE has a measurement of 4. Actually, I'm going to change FE to 6 just to make this a little bit of an easier sample. So I have DE has a measurement of 4, EF has a measurement of 6, and DF has a measurement of 8. Okay? That means for that specific triangle right there, I know all of the side lengths. Now over here, we get a little bit smaller, and for the sake of an easy example here, we're going to go ahead and just say that GH has a side length of 2, HI has a side length of 3, and I have no idea what GI is. Don't know. Here's one way that equivalent ratios are going to help us out. They can help us by finding missing measurements, missing values for sides of a triangle. Okay? And the nice thing is, since I'm going to be setting up 2 equivalent ratios, I don't have to worry about all 3 sides. I just have to pick a side that's known and the side that's unknown. Here's what I mean by that. I have no idea what GI is. You may have an idea just by looking at it because you're smart, but let's pretend that we just don't know. Okay? We have no idea. So I want to make sure that GI is one of the sides that I deal with, because that's what I want to know. Always start with what you don't know, because then you can work backwards. What is the corresponding side for GI? Based on what we just talked about, if I want to know this, what is GI's corresponding side? Did you say DF? Yeah? These 2 sides are corresponding, right? So the ratio that I write here is going to have GI, because that's what I picked first, and it's going to have a ratio of, or the other part of the ratio is going to be DF. So here's my first ratio. Now pick any other side, okay? You don't have to use both remaining sides, just pick one, and either way it'll work. So I'm going to go ahead and just pick GH, because why not? So I have this ratio here, and I'm going to put an equivalent ratio over here. Now since I started with the little triangle first on top, I have to do that with the second ratio, okay? So this second ratio here has to start with the little guy. So I'm going to go GH on top, and then go over to the bigger triangle here, which goes on bottom, and the corresponding side for GH is this one, because they're both on the bottom of the triangles, right? So there's the second ratio. These are both equivalent ratios, so this right here is a proportion, all right? And a proportion, as we kind of figured out in the first part of this lesson, can help us figure out missing values. And in this case, we're trying to find a missing side length, which is right here. I'm sorry, right here, okay? So let's go ahead and rewrite these ratios, but let's put in the actual values instead of the names. GI, I don't know. No idea. DF, though, I do know. DF is this guy, and that's 8. Okay, so here's this first ratio rewritten with values, at least the values that I do know. Now this second ratio here, on top has GH, and that's this one. That's got 2. And DE here, its corresponding side, with a measure of 4. Okay? This is a proportion that I can work with. A couple of ways to do this. First of all, I can figure out, since I don't know this, I'm going to have to figure out what do I do to this 2 to get this number. And the bottom of this proportion is going to tell that to me. It's going to help me figure that out. What do I have to do to get from 4 to 8? Okay, think about that. Well, I'm getting bigger, so I'm not going to divide. I need to multiply something. What times 4 gives me 8? 2, right? So basically, I'm going backwards here, but 4 times 2 is 8, okay? So if I do that to the bottom part of this proportion, I have to do that to the top as well. So 2 times 2 is, what's the question mark? 4, okay? So here, 2 times 2 is 4. I'll replace my question mark with the number 4. Does this look like it probably works out okay? And remember the tests that we can do to make sure? Well, we just did one here. And we can also do the cross multiply test to make sure this works. 4 times 4 is 16. 8 times 2 is 16. So we know that this is a nice valid equivalent ratio. and it looks like we did everything right. So this up here has a side measure of 4. Okay? So there's a great thing that equivalent ratios can help us with. If we have two similar triangles, and remember this really only works with similar triangles, we can find missing side lengths. And that's kind of important. All right, I'm going to clean this up a little bit. Get rid of some of these measures. I'm actually going to get rid of this small triangle, but I'm going to keep the big one. So if you want to go ahead and draw one more triangle, don't make it too small, because here's what I'm going to do. I'm going to go ahead and name these A, B, C, but then I'm going to draw another triangle inside of it. And the way I'm going to do that is I'm simply going to draw that line down there. This is like one of those puzzles. How many triangles do you see? Hopefully you see that there's a big triangle on the outside and then a little triangle on the inside. So the only thing I need to do now is give this 2 more labels so that you can see that there's an ABC triangle and an ADE triangle. Okay? And I'm going to give you a fact. The fact is triangle ABC is similar to triangle ADE. Really, the reason I write this down is just to tell you these two triangles are similar. And once I tell you that two triangles are similar, that means you can work the magic that we just worked, okay? Now I'm gonna go ahead and give these side lengths some measurements as well, okay? And I'm gonna do it over here so that we can keep track by looking, so this doesn't get too messy and muddy, all right? Let's look at the big triangle first. And I'm going to say side AB, has a measure of 6. Okay? Side BC, right here, has a measurement of 8. And finally, this side right here has a measurement of 10. Okay, so that's the big triangle. That's this guy right here. The little triangle inside has measurements of, well, here's AD. Let me kind of block this off so it doesn't get in the way. AD has a measurement of 3. DE, which is cutting this thing pretty much in half, DE has a measurement of 4. And finally, AE, right here, has a measurement of 5. Now again, you're probably thinking, oh, I can totally see what's going on here, but I want to keep the examples simple just so you can see the process that's happening and the fact that just because two triangles are embedded doesn't mean that they're not similar or that we can't work the magic inside, okay? So, let's just say that we didn't know, we do, but let's just say that we don't know the measurement of AD, this little guy right inside, okay? I don't know this side length, but that's okay. Now, first of all, if you noticed, when I was writing all of this list right here, I was writing them in order so that I could see which ones correspond to each other. So this first one that I wrote for both triangles, they correspond with each other. AB corresponds with AD. Okay, so these two top ones correspond, these two middle ones correspond, and finally these two last ones correspond. Now remember, I always want to include this, the unknown, in my first ratio, or at least one of the ratios. So I'm going to go ahead and say side AD over its corresponding side, which is this one, right? And then my second ratio of my proportion, which has to be equivalent, pick one. It doesn't really matter. Let's go with AE this time. The corresponding side for AE, since AE is right here, I need to pick AC. Okay, so that's my setup. Now I'm actually going to use the numbers. AD has a measure of, we don't know, even though we do. AB has a measurement of 6. AE, down there, has a measurement of 5. And finally, AC has a measurement of 10. Okay? Now, we already know the measurement of AD, because I showed it to you earlier. But look at this ratio, this set of ratios, these equivalent ratios, and this proportion. It looks a little different because it's harder just for me to look at this bottom set right here and say, oh, I'm going to multiply 6 by what to get 10? It's going to be a decimal, and that doesn't sound too friendly to me. The reason I set this up is because I want to show you a different way you can do this. You can also figure out what happens here. Look at just this ratio, and it can help us figure out this ratio, okay? Instead of going sideways, now I'm going to go up and down. And the question I'm going to ask myself is, what do I have to do to 10 to get to 5? Because the question should also be on this side. What do I have to do to this 6 to find out this missing number? So over here, let's look at this ratio first. What do you do to 10 to get to 5? This time you're getting smaller, so we can't multiply. I mean, we could multiply by 0.5, but that's not fun. So what are we dividing by 10 to get 5? Or what are we dividing 10 by to get 5? 2, right? We're gonna have to divide 10 by 2 to get 5. Now, if I divide this side by 2, I have to divide this part by 2 as well. What is 6 divided by 2? 3, right? Is that what we had at first? You remember before I erased it? Yeah, that works. Excuse me. And now that I have a completed proportion, there's a couple of different ways I can test that. The easiest way, since I don't want to deal with decimals, is to go ahead and look at the cross multiply. 3 times 10 is 30. 6 times 5 is 30. So I know that I have a good answer here. I have a good solid proportion. All right? So there's an embedded example. Now let's do a problem. Okay? I'm going to erase all this stuff. Excuse me. Got a little dry throat tonight. Okay. Here's my problem. Here's my scenario. I've been told, and here's me, I've been told to go outside and figure out how tall my biggest pine tree is. Okay? I want to make sure that we're kind of standing on the same ground here, so I'm going to erase me real quick and redraw me here. We're both standing on the same ground, me and this tree, and I need to figure out how tall this tree is. Now, I'm not going to climb this tree. If you've seen a really big pine tree, you know they're really tall, and if you know anything about me, you know that I'm desperately afraid of heights, so I'm not going to climb this tree and like carry a tape measure up with me or anything like that. Not going to happen. So what I'm going to do is I'm going to use this tool. I'm going to use our sun. Hopefully it's a nice sunny day, because on a nice sunny day, what do objects create thanks to the sun? Well, the sun's light shines down here and it creates a shadow, right? Now here's the cool thing. If I'm standing close to this tree, me and the sun, or me and the tree, are generally going to be affected by the sun in the same way. So our shadows should be proportional. Okay? Sun rays shine down on things and they make shadows. Okay? Starts on the top of my head and makes a nice little shadow on the ground right here. So my shadow is basically from my feet to here. Do you see how this makes a triangle? I'm one of the sides of the triangle. My shadow is the other side of a triangle. And this invisible side right here is supposed to be the sun's rays coming in at an angle and creating my shadow. The cool thing is, the same thing happens with a tree. So the sun, and I'm going to try to make this kind of look like the same angle. The sun also creates that invisible line right here for this tree, which casts its shadow on the ground. It makes another triangle. For this exercise, please ignore the fact that these triangles don't look that similar, because I'm not the perfect artist, but for now we're going to assume that me and this tree are creating similar triangles, okay? So here's what I can do. First of all, I know me. I am 6 feet tall. So my side right now is 6 feet, okay? Then I'm gonna go out here and I'm gonna measure my shadow. And we're going to assume that when I put the tape measure down and measured my shadow, it was 9 feet, okay? Do I really need to know this? Remember when we were dealing with those other triangles, all we really needed to know was the unknown and one other corresponding ratio. So I really only need my height and my shadow. I don't really need this. So I'm not going to worry about measuring from the top of my head to the point of the shadow. I could, but why? So then I go to the tree. Now again, I'm not going to climb this thing and measure it. That's out of the question. So this is going to be an unknown. I don't know how tall the tree is, but I can take my tape measure, put it at the base of the tree, and extend it out here, okay? And when I do that, I find out that I have a 27-foot shadow for this tree, okay? Can you kind of get an idea of what to do next? Well, I have 2 similar triangles, and these 2 triangles have corresponding sides. First of all, my height and the tree's height are corresponding, okay? So if I wanted to go ahead and write a ratio from me to the tree, I said me first, so I have to go on top here. But I don't know the tree, so there's my first ratio. So the second ratio will be corresponding shadows. Here's me. Here's the tree. Okay? Just like we've been doing all this time. But this time it's pictures. Okay, so now my job is to find out how tall this tree is. I need to find this missing value right here. Okay? I could go this way, but if I multiply 6 times something to get 9, that's going to be either a fraction or a decimal, so let me try this other way first. Okay? How do I get from 9 to 27? 9 times 3 gives me 27, right? So if I multiply this part by 3, I have to multiply this part by 3 as well. Okay? And if I multiply 6 times 3, then that gives me 18 for this number. And that shows me that this tree out here is 18 feet high. Pretty cool, huh? So I don't have to go climbing trees. All I have to do is figure out some interesting way to use shadows and the sun and proportions to figure out how tall that tree is. Am I going to be totally exact? I'm going to be pretty close. There have been many, many measurements made this way in history, including a long time ago, a guy named Eratosthenes actually figured out how big around the world is using something similar to this. So you have a new power. You have a new superpower. You can figure out unknown quantities, unknown heights using proportions, using equivalent ratios. And now I want you to practice, okay? there's 2 worksheets that I told you for practice, for exercise, underneath this video. There's one for the equivalent ratios. You may have already done that one after watching the first video. The second one is all about triangles, okay? So go open that up, do some work on it, and let's see how you do. When you're done with both of those worksheets, then you can open up the exercise review video, because I will be reviewing both videos in that, or both worksheets in that one video. Okay? That was fun, huh?